Starting to this new section, assignment 1. This is a preposition. A system of vectors v1, v2, v3 up to vn of vector space v over f is the basis of v if and only if each element of v can be uniquely expressed as a linear combinations of these vectors. Here the word uniquely is very important to note because it is a two-way proof. It is given to us that if these vectors are the basis of v, then I have to prove that these can be uniquely, every element of v can be uniquely expressed as a linear combinations of them. But because these are the basis of v, it is clear that every element of v is expressed as a linear combinations of these vectors. But I need to prove the uniqueness over here. So for that, I have to choose one more other kind of scalars, right? So you will see in the proof. And the other way is, if every element of v can be uniquely expressed as a linear combinations of these vectors, then I have to show that those vectors are basis for v, right? So it is a two-way proof. Let's start. Suppose the one way, these are the vectors, these are the basis for v, right? And because v1, v2, v3, these are the basis for v, then these are linearly independent also, right? Okay. Now because these are the basis for v, then every element of v is a linear combinations of v1, v2, v3 up to vn, right? So therefore, if I take an element from v, then that v is expressed as a linear combinations of these vectors alpha 1 v1 plus alpha 2 v2, alpha 3 v3 up to so on alpha n vn. Right. Now I need to prove the uniqueness part. If possible, let me take the other kind of scalars beta 1, beta 2, beta 3, right? Other than alpha 1, alpha 2. So let v is also equal to beta 1 v1, beta 2 v2 plus beta 3 v3, so on beta n vn, right? Where these beta 1, beta 2, these all are from f. Okay, then just see these two equations from 1 and 2. This v can also be written as this one. So I am writing instead of v on the left hand side alpha 1 v1 plus alpha 2 v2, so on alpha n vn. This is equal to beta 1 v1, beta 2 v2 up to so on beta n vn. Now taking this beta 1 v1 to the other side and taking v1 common, so this will become alpha 1 minus beta 1 v1. Then this is alpha 2 minus beta 2 v2, so on alpha n minus beta n. Vn equal to 0. Now if you notice that this v1, v2, vn, these are given, because these are the basis for v, so these are linearly independent. And because these are linearly independent, so these scalars, the differences, these are all equal to 0, right? So because since v1, v2, vn are linearly independent, which means all the scalars are 0. Now if this is 0, then this implies alpha 1 is equal to beta 1, alpha 2 is equal to beta 2, so on alpha n is equal to beta n. Right? So thus every vector of v is uniquely expressed as a linear combinations of v1, v2, v3 up to vn. This is proved because alpha 1 is nothing but beta 1 Both are equals, which means uniqueness has been proved. Now the other way, the converse part. Suppose every element of V is uniquely expressed as a linear combinations of V1, V2, Vn, and we need to prove that these vectors forms basis for V. Now since every element of V is expressed as a linear combinations of these, which means all these are the generators of V, first condition is proved for the basis. Yes. So V is generated. We can say that therefore V is generated by V1, V2, V3 up to Vn. Now to prove that these are linearly independent, right? Because we have to prove that forms basis. Now to prove that V1, V2, V3, Vn are linearly independent, let's take the linear combinations of them first. We have taken and this is equal to 0. Also, can I write 0 V1, 0 V2, 0 V3, so on. 0 Vn is equal to 0. Can I write this? Yes. Yes, I can. I just multiplied 0 with V1, then multiplied 0 with V2, then added to 0 multiplied with V3. So I can write like this. Okay. Now since 0 is the element of V, yes, because V is non-empty, 0 is the element of V. So therefore, because it is given to us that every element of V is uniquely expressed as linear combinations of this, which means this 0 is, because 0 is belonging to V, 0 is uniquely expressed as a linear combinations of these vectors, right? So from 3 and 4, what can we say? We say that this alpha 1 is equal to 0, this alpha 2 is equal to 0. Just look at 3 and 4, what you are judging that? This alpha 1 is nothing but 0, alpha 2 is also 0, alpha 3 is also 0, alpha n is, all the alphas are 0. So from 3 and 4, alpha 1, alpha 2, alpha 3 up to alpha n all are 0, right? So therefore V1, V2, Vn are linearly independent. Because these are all 0. So V1, V2, V3, all these are linearly independent. It is shown now. Since these are linearly independent and V is generated by them, both the rules are satisfied to prove basis. So therefore V1, V2, V3 complete set of these vectors is a basis for V. Okay. Just keep in mind two things. How to prove that these vectors are bases. You just have to prove that every element of V is expressed as a linear combinations of the vectors given. And second, you need to prove that these vectors are linearly independent. If these two conditions satisfied, we say that such vectors are basis for V. Right? Here the difference is just the term for uniquely expressed. The term uniquely. Right? So this is your preposition. Thank you so much.